It's also, yeah.
Oh, I was in high school. I
It's all right.
Right at left here.
No, not but I've only been to student. Okay.
And then
Isn't it weird? It
afterwards,
sounds like it's coming from my laptop.
like lateral.
I think here, but my laptop is like.
That's like ridiculous.
Yeah, I mean, that makes sense. Like, it's not like you care. It's just gonna be hard. You're already doing that.
Oh, yeah.
I had to do.
Well, I did, and it's still,
Is
like a short.
Yeah, I know. I'm into it.
I can hear myself. I was like, is there a way to get?
Do you think
totally
you-
shut it off?
I think you should probably do it. I think you will be.
I was like, no, I
it's
read
wrong.
it there. I got
Like, you had the right.
It doesn't even make sense. I consider like the like extra credit.
No, it's not. Not.
Like it's see some.
You see it.
I think it's a good stuff.
Oh, we use this. Everything. Oh. That's
I could try disconnecting it. It's kind of late.
Yeah, I know. I'm glad you. Never mind.
I've never had to do this.
Yeah.
I mean, I hear it coming from.
Oh, that's what
Maybe you want to connect.
Yeah.
Yeah. I think everyone is taking the class. What they're doing.
So he did.
Okay, but you should say. How it works. It's like, basically yeah, of course. Basically, like, yeah, so like the end of my essay was literally now. Just got like.
Okay. Okay, so I think we can get started. I mean, just wait 30 seconds for them to get a call.
Very weird.
All right, so today we have Dr. Jessica Shaw from our laser laboratory of energetics, not from very far, but about a mile away, I think, in here. Jessica got her master's and PhD in electrical engineering from the University of California, Los Angeles, UCLA. And after her PhD, she, I think, started the job right here in the laser lab, if I understand. She was here for 6 years. She works the most experimental work for short pulse laser plasma interactions. And more recently, she has been working on plasma based laser amplifiers. I guess Raman amplifier, right? Raman amplifier. And so we'll hear that today.
Thank you. Thank you very much for the introduction. Good afternoon, everyone. I'm very excited to be here. It's great to come to campus and be able to talk about the work that we've been doing. So I'll be talking about 2 different projects that we currently have going on, both our plasma-based laser amplifiers and our plasma-based particle accelerators. Before I start, I have to acknowledge my collaborators. We have a big team at the LLE who's working on this, both from the laser side and from the plasma side. And then we also have our collaborators at Los Alamos National Laboratory who've been working with us on the electron radiography work that I'll talk about, and also collaborators at Lawrence Livermore National Laboratory that we work with on our laser plasma accelerators. So to summarize what I'll cover today, the University of Rochester's Laboratory for Laser Energetics is growing its program in ultra-short pulse laser plasma interactions, including the Raman amplification and laser plasma accelerators that I'll talk about today. Raman amplification of laser pulses in plasma is a very exciting path towards overcoming the single beam intensity limit of today's solid state-based laser amplification. I'll talk about our initial experiments that have demonstrated Raman amplification in a single pass configuration with an amplification factor of 12.6 and efficiencies as high as 7.4%, which is the highest that's been recorded in experimental work till date. And then I'll talk about our laser plasma acceleration work, where we're looking at a case where we're accelerating particles using laser-driven plasma waves. And this boasts acceleration gradients that are 3 orders of magnitude higher than our traditional particle accelerators, and therefore may provide a path to a compact tabletop source of electrons and hard X-rays or gamma rays. I'll talk about 2 different parts of this. Our experiments on Omega EP, the laser at the LLE, have demonstrated electron beams with maximum energies that exceed 200 MeV, charges greater than 700 nanocoulombs, which is a lot of charge, the highest recorded to date from a laser plasma accelerator, and conversion efficiencies from laser energy to electron energy up to 11%. And then I'll talk about the work that we're doing with those electron beams, where we're demonstrating a novel radiography method, electron radiography, with resolutions as low as 100 microns. Great, so diving into part 1, Raman amplification. So this is work towards a plasma-based laser amplifier. So why are we interested in this? And that is underlined by the fact that the realization of intensities beyond 10 to the 23rd watts per centimeter squared using Raman amplification in plasmas promises a breakthrough in high energy density physics. It'll come as no surprise that exploration at the intensity frontier has always offered new avenues for physics. And in particular right now, intensities in this 10 to the 23rd range would provide the ability to test quantum electrodynamics in the currently unexplored low energy strong field regime, where they predict signatures for new physics to arise. However, today's present day petawatt class lasers can only provide focus intensities up to 10 to the 22nd watts per centimeter squared on target. And that's because today's current laser technologies appear to be fundamentally limited to these intensities by the damage threshold of the compression gratings. So our petawatt class lasers require femtosecond pulses, and we have to compress these pulses by broadband gratings with gold coatings. And currently those gold coatings can only sustain fluences on the order of 0.15 joules per centimeter squared. So unless there's a major breakthrough in gold coatings, if we want to go to a more intense laser, we need an unfeasibly large gratings. So by amplifying and compressing a laser pulse directly in a plasma instead of in a compressor, this would remove this damage fluence constraint and push us towards this 10 to the 23rd watts per centimeter squared. So how exactly are we doing this in plasmas? Raman amplification uses a plasma wave to transfer energy from a long energetic pump pulse to a shorter seed pulse through the 3-wave instability of stimulated Raman scattering. So if we have our pump beam and our seed beam counterpropagating, when they overlap in a plasma, they set up a ponderomotive beat wave that can drive an electron plasma wave. And that electron plasma wave, under the right conditions, will transfer the energy from the pump to the seed, thereby depleting the pump and amplifying the seed. This is ideally what it looks like on one slide. This is what it looks like in practice for us in experiments. Our Raman amplification experiments utilize 3 separate single pulse laser systems to bring an intense seed to a preheated plasma. So our experiments start in a Mach 5 2-millimeter gas jet that is firing a 95.5 mix of nitrogen methane. And we propagate in a heater beam. It's a narrow band laser, 532 nanometers, 1.3 nanoseconds, full width half max. And we fire about 3.5 joules on target. So that heater beam comes in, ionizes our plasma column, and then at some time later, so typically between 5 and 9 nanoseconds, we then bring in our pump and our seed in a counter-propagating geometry. Our pump is a 1053 beam, 8 nanometers bandwidth, full width half max, typically running between 25 and 30 picoseconds. And we can vary its energy, so we can produce intensities up to 2.7 times 10 to the 16th on target. Our seed is a pretty unique wavelength, 1170 nanometers with 200 nanometer bandwidth. We typically run it at 135 femtoseconds, full width half max. And it can be on target with intensities of 110 to the 15th or higher. On every shot, we, after the pump goes through the plasma, we measure the transmitted energy. Typically we'll get 45%. And we also measure the backscattered energy and the spectrum, which gives us important information about our plasma. And then also with the seed, we'll measure the transmitted energy and spectrum. And so the work that we've done so far, we've been looking at the scaling of both the amplification factor and the efficiency with pump intensity. We find that the amplification factor scales approximately linearly with pump intensity for intensities up to 1 times 10 to the 16th. Our amplification factor, we define as the energy out of the seed over the energy in. And for the seed energy out, we have to look at the total energy that's coming from our plasma and subtract off it our average backscattered energy for our pump, because we need to take into account that noise. So this is the plot of the amplification factor versus pump intensity for our 2 different heater pump time delays. And we can see this approximately linear scaling up to that point of 1.2 times 10 to the 16th. That point gave us our maximum amplification factor of 12.6. And then when we pushed our pump intensity beyond that, what we saw was that our amplification factor rolled over and became highly irreproducible. We also looked at how the efficiency scaled with pump intensity. We define our efficiency as the energy that the seed gained divided by the energy in the pump that was temporally overlapped with the seed. So if we look at our efficiency as a function of pump intensity, we see that it actually peaks at a lower pump intensity of 3.310 to the 15th. That gave us our maximum efficiency shot of 7.4%. And then again, when we pushed our pump intensity higher, we saw that the efficiency rolled over and again became pretty irreproducible. We've also looked at scaling with the seed intensity, and our experiments are uniquely situated to do this because prior Raman amplification experiments have had very low energy seeds that could not be easily tuned, versus ours that has a high intensity seed that we can tune the energy of. And we saw that the maximum amplification factor scales inversely with seed intensity, and it shows very high shot-to-shot variation at these lowest seed intensities. We also see that the efficiency is scaling approximately linearly with the seed intensity, and it shows a much stronger scaling for our 9 nanosecond points than for our 5 nanosecond points. So that is where we are. We're still very early in these experiments. And for our current and future work, we're actually currently in the middle of a 3-week Raman amplification campaign with the goal of further improving our efficiency. Thankfully, we don't shoot our lasers on Monday, so I'm here. We're testing 3 new concepts to improve efficiency. One of the things that we're looking at is to change our gas mixture from a 95-5 mix of nitrogen and methane to pure hydrogen. And the goal here is to try to improve the pump propagation. If we're able to improve the pump propagation, there'll be more pump energy available for the seed, and that should hopefully improve our efficiency. We're also altering the focal geometry of our heater beam to get a hotter plasma before the pump and seed arrive, which should also improve our pump propagation. And finally, we're exploring the ability to vary the pulse duration of the seed, which simulations predict should improve efficiency. And so that actually brings me to part two. Yes.
Sorry, I just have like a procedural question for how you guys do these experiments.
Yes.
If you just have this exposed gas jet, that's your amplifier, how do you prevent like back reflected power damaging your pump and your upstream amplifiers if you have no like AR coating or anything like that?
Yeah, this is a very good question. And thankfully in our system, the amount of backscattered energy that we get is small enough that if it were to come back with exactly the same focal geometry as it enters, the fluence on any of the optics would be small enough that it would not damage the system. And if it does change, so often we'll see our backscattered light will come back with a different F number. And we have a series of pinhole, like spatial filters, like pinhole filters that will clean that out. But this is a very big concern especially as you start moving into a lot of the really high intensity work that the laser lab is moving towards. Like, how do you deal with backscattered light? Because as I'm sure you know, many lasers experience a lot of unintentional damage that way. I won't talk about it here, but we had that problem on some of the shots I had on EP, and we put a hole in one of the gratings, which was not very good. Yeah. Any questions on part one before I?
So I have a question that the gas picture you're using, there are two gases right now that we were saying.
Yes.
Which one is being used for Raman amplification? I mean, I assume it's still the oscillations of the molecule that is giving you Raman shift. I'm assuming that, right? So
in our case, we're not using our gas to get a Raman shift because we come in, let me go back to.
Yeah, so that's what, if you use something else, why do you go Raman amplification then? Because you're not using molecular vibrations,
Right, yeah. So the reason that it's called Raman amplification in this particular context is that the three-wave instability, like the plasma-based instability, is stimulated Raman scattering. And because it's named after that instability, so it's same name, but
So what's the role of the molecules then?
Yeah, so in our case, the molecules don't exist anymore. They're all completely ionized.
That's what I thought, right? They're ionized, but they're together, they're still molecules, they're atoms now.
No, they're atoms.
They're atoms. Right?
Yeah.
So there are no molecules.
No molecules, yeah. All the energy transfer is mediated by the electron plasma waves. So it's the electron plasma, like just free electrons that do all the mediation.
I never used the word Raman amplification. Raman, you in that context.
Yeah, it's very, very different. And it's just interesting, right? Because there's so many different phenomena with that name. But yeah, in our case, we just have a pure electron plasma, well, not a pure electron plasma, but that's functionally what's doing all these.
So there is no, there's a wave here, which is electron oscillation, I guess.
Yes.
It's plasma electron oscillation.
Correct.
And so what determines the frequency shift? The speed of the electron so what gives you frequency shift? Like your seed will have a shift of the frequency from the pump. In nanometer, that was about 600 nanometer, I guess.
Yeah.
Right, something like that, 600 nanometer, something of that kind. So what determines that shift?
Yeah, so in order to to go from our pump wavelength to our seed wavelength, we have to K-match in the plasma wave. And so for Raman amplification to work, you have to have your pump and seed, like based on the pump and seed wavelengths, you actually set your plasma density such that the plasma frequency will K-match between the pump and seed.
So there's a phase match.
Yes.
So you're saying the phase matching because Raman does not require phase matching.
Right, yeah.
That's a strange concept, but there's a phase matching here. It's more like a photo mixing, somewhere.
Right, yeah.
Okay.
Yeah.
Okay.
It's a very different than what you think about, yes. for sure.
All right, yeah.
Hi, Jessica. This is a C Chun here.
Yes.
Yeah,
online.
I do have a question. I'm just a bit lost. I think I got lost in the steps. What are we measuring or what are we doing here?
Sure. Yes. So what we're looking at right now is when we bring in our two beams, so our seed is about 10 millijoules on target. And the first step that we're looking at is how much energy we can actually transfer from our pump into our seed. So the primary measurement that we've made in our initial experiments is we measure the seed. So if it comes in with 10 millijoules, if it exits with 120 millijoules, then we've amplified by a factor of 12. So here, when we look at our plasma on any particular shot, we want to know how much of our pump is transmitted through. We want to know how much of it is backscattered, because any of that light that's transmitted through hasn't been given to the seed, so it's an inefficient pump. And any of the light that's backscattered also isn't available for the pump, so that's like wasted pump energy. And additionally, because it's backscattered in the same direction as the seed is traveling, that's a source of like noise on our detector. So right now we're just measuring the energies in and out of each beam as a first step. In our upcoming, yes.
I bet. I think I asked the question poorly. Is this all just for developing new amplification techniques?
Yeah, so right now we're very much looking at the basic physics of Raman amplification in plasmas. In computational work and in simulation work, it works beautifully. You get 90% energy transfer from your pump into your seed. You see your seed is beautifully compressed to high intensities. It maintains good focusability after amplification, like everything that you would expect from a standard solid state laser amplifier. In experiments, this is one of those experiments that has been a holy grail that people have been chasing for 30 years, and it is really freaking hard. I started on this project right out of grad school, and I didn't fully understand how hard these experiments are. And so one of the things that we're looking at the LLE that's different than prior experiments is to really understand the nuances that have caused all the prior experiments to not fall, but fail or not produce kind of these ideal parameters. So one of those, let me go back. I talked about our seed being very intense, 10 to the 15th. Most prior experiments have started with a seed that was barely above noise. So they have to let that seed grow from noise and evolve for very long distances in plasmas. And if you've ever tried to propagate a laser through plasma, it does not like to do this well. So when you're letting your seed just grow from noise, they're like just that starting point already setting you up for failure. The other thing that other experiments haven't done is pay very close attention to how both their pump beam and their seed beam propagate through the plasma. So here, when I said our transmitted energy is only about 45%, that is true even if we don't fire the seed. So it's not like 55% of our energy is getting transferred into the seed. We're losing, as this pump is propagating through the plasma, either due to ionization-induced refraction or filamentation, we're losing most of that pump energy. And we're one of the first experiments who's actually even looked at it. We haven't figured out how to fix it yet, but we at least know that it's going on. Prior experiments have kind of just covered their eyes and pretended this is not happening, and then they wonder why their efficiency.
What is the length of the plasma column there?
Yeah, so we have a Mach 5 2-millimeter jet, so we shoot about 1.8 millimeters above, so it's about 2.7 millimeters long where the lasers are.
So you're getting a factor of 12 amplification of that, but just 2 millimeter long.
Yeah.
That's pretty good, actually, I would say.
Yeah, it's not, well, especially because we're starting with respectable energy.
That's right.
Yeah.
If you are in the linear regime, you're not the exponential amplification. You are
Right.
in the linear regime because you're saturating everything.
Exactly.
You are linear.
Yeah. So some of the prior work that have started with like a seed from noise, they'll show one paper showed amplification factor of like 10,000.
Yeah, you can.
But yeah, you start with nothing.
In the noise to get 10,000, nothing.
Right, yeah,
Nothing.
yeah, exactly. So, yes.
Do you have any kind of like inhomogeneous broadening of the amplification bandwidth because it's a plasma, or is that covered by the fact that like it's all moving in one like Doppler broadening or something, or is that removed by the fact that it's all going in like one direction?
Yeah, so this is a very good question. So we do see when our seed propagates through our plasma, we do see that its bandwidth changes versus when it doesn't go through a plasma. For us, that is going to be more due to self-phase modulation, typically through our plasma, rather than any sort of Doppler broadening. But yeah, due to the propagation effects, we do see that change. And one of the things that we're trying to look at probably in our January experiment is how that change in the bandwidth affects the compressibility of the seed after we amplify it. Because one of the things we're wondering is if this additional bandwidth, even though it, functionally is more bandwidth, actually makes it less easy to compress because it's spectrally incoherent.
You're still compressing after this amplification? Because I thought the whole point was to remove the compression stages.
Yeah. So no, we're not putting it separately into a compressor after, but we have not yet measured the seed pulse duration. Okay. Like we know our pulse duration going in, we haven't measured it after. Gotcha. Turns out that is also a very challenging measurement that we are, because right now we have a spider post plasma to measure our pulse duration. And it works beautifully when you don't fire the gas jet, but as soon as you turn on the plasma, there's a lot of noise in the spider signal. So we haven't been able to sort that out yet.
Thank you.
Yep. Any more? No, okay. I can, of course, take more questions on this at the end if they strike you. All right, now I'll move into part 2, where I'm going to talk a bit about our laser plasma accelerators. So part 1 was how we're trying to make more intense lasers. This is more what we're currently doing with the intense lasers that we have. And as I kind of started beginning, we're really looking towards developing tabletop electron, X-ray, and gamma ray sources. So I want to start by talking about why we study laser plasma accelerators, because it might not be very obvious why we're interested in this. And to understand that, you really have to take a step back and look at our conventional radio frequency accelerators, which are key scientific tools in many physics fields. So here's an aerial view of the SLAC National Accelerator Laboratory. And in its heyday, it had a 3-kilometer long electron linac that produced electron beams that were 40 GeV, so very high energy beams. And then not only are the particle accelerators key scientific tools, but today's most advanced X-ray sources also rely on these kilometer scale electron accelerators. So SLAC has now taken its 3-kilometer long linac and broken it up into 2 1-kilometer long sections to drive LCLS-1 and LCLS-2, which are arguably the most advanced X-ray sources in the world. And so the question that the laser plasma accelerator community is asking is, can we develop a high-performing compact electron and X-ray source? And to answer this compact part, you really need to look at your acceleration gradients. So SLAC is accelerating electrons at 10 to 20 megavolts per meter typically. And if you look at a plasma, it can accelerate particles at over 40 gigavolts per meter. So we have more than 3 orders of magnitude improvement in our accelerating gradient. So that lets you ask the question of, can we swap 20 to 40 meters of RF cavities for just 4 millimeters of plasma? It would be ideal if we could. So how exactly does this work? Laser wake field acceleration, which is our laser plasma accelerator of interest, is somewhat analogous to wakeboarding. So I don't know, many of you probably have seen some sort of talented wakeboarder out on the lake. So we have a wake and water. It's meter scale in this case. We have a wake driver, our boat. We have a wake field, which in this case is a height modulation. You have gravity as your potential energy source. And then you have your talented wakeboarder who's caught that wake and is being accelerated and will continue to accelerate until his velocity exceeds that of the boat. We have the analogous situation in our plasma, where now we have a laser as a driver instead of our boat. And now we have a density modulation. So this laser is expelling the electrons out by the Ponner motive force. It's typically fast enough that your ions remain immobile. So your electrons rush back behind the laser and set up this density modulation. That density modulation produces a longitudinal electric field. So you can trap electrons there and accelerate them. So then the question becomes, okay, this is great. What if we need even more charge in our laser plasma accelerator? If you want more charge in your laser plasma accelerator, instead of driving with an intense short pulse laser, you're going to drive with a picosecond kilojoule class laser. And we call this now self-modulated laser wake field acceleration. And here we take the laser pulse where your pulse duration is longer than your plasma wavelength. And it'll enter the plasma and it becomes modulated at the plasma wavelength via the Raman-Ford scattering and or self-modulation instabilities. So Raman has to keep popping up over and over again. Those modulations lead to a train of laser micropulses, and they'll coherently drive a plasma wave. And again, the longitudinal electric field will trap and accelerate electrons to relativistic energies. So now in this case, instead of having just one plasma wavelength that's trapping charge, you can see we can stack them. So we can get a lot more charge this way. And then also in this case, because your drive laser is now overlapping the trapped electrons, you actually get a second acceleration mechanism known as direct laser acceleration, in addition to your laser wake field acceleration. And how that works is as your electrons are being accelerated, they're also executing what we call betatron oscillations. These are a synchrotron oscillation because the electrons are seeing the restoring force of the ions because all the electrons have been expelled by the drive laser. And so as those electrons oscillate transversely, the transverse laser field can increase their transverse momentum. And that increased transverse momentum can be converted to increased longitudinal momentum through the V cross B force of the laser. All right, so we're now producing high energy electron beams. We have a lot of charge because we're looking at a self-modulated laser wake field accelerator. So why do people want these high charge sources of high energy electrons? And for us, this is really driven by the use of these sources for radiography of other physical phenomenon. I'll talk about two big motivators, these hard bright X-ray sources and also electron radiography. So we can use our electron beams to make hard bright X-ray sources through three different mechanisms. So betatron X-rays are emitted as our electrons are executing these transverse oscillations. Every time they change direction, they're going to emit a photon. So that's how we get betatron X-rays. We can also take our electrons and laser beam and reflect them off a plasma mirror. The reflected laser will collide with our electron beam and produce Compton X-rays. And then finally, we can take our electron beam and slam it into a high Z converter. And then as those electrons are bent by the high Z nuclei, they can emit Bremsstrahlung X-rays. So we can make X-rays through these three different mechanisms, but if we look at all three, the number of photons you get are proportional to your number of electrons. So if you really want these bright X-ray sources, you need to make a lot of electrons. And then on the electron radiography side, this is a really new application we've been looking at using the electrons from the laser plasma accelerator. So you take your electron beam and you propagate it through some material that you're trying to interrogate, and those electrons will undergo multiple Coulomb scatterings. And based on the scatterings of the electrons, you can determine the density and different features in your probed material. So our laser plasma experiments that are based on self-modulated laser wave field acceleration and direct laser acceleration were performed on the Omega EP laser at the Laboratory for Laser Energetics. We bring the beam in its 1 micron form, best compressed at 700 femtoseconds, 10 to 95 joules on target, which gives us an A0 of 1.3 to 6.7. For those of you, probably no one here thinks about A0 on a daily basis. This is our normalized vector potential, and it's important in our field, but think of it as it's proportional to the square root of intensity. So your peak laser intensity, you can think of A0 in the same terms. So for A0s of 1.3 to 6.7, this is an intensity of 0.2 to 5.5 times 10 to the 19th watts per centimeter squared. We focus our beam with an F2 off-axis parabola. We apodize it to F5 or F10, focus at 500 microns inside our Mach 5 gas jet that's firing pure helium. We ran with different nozzle diameters, 2 to 10 millimeters. And then the transmitted laser and the produced electron beam propagates 40 to 50 centimeters downstream, where it's then collected by our EPPS. This is our electron, positron, proton spectrometer. On the front, it has 12.5 microns aluminum to dump the laser, and then 2 MS image plates. And these image plates let us measure the transverse beam profile and the total charge in each electron beam. The electrons then go inside the body of the EPPS where they're dispersed so we can measure our energy spectrum. Here's a sample spectrum. You can see that we have electron energies that are just a continuous energy spread out over 200 MeV, which is the energy limit of our detector. So we wanted to understand how the total charge in the electron beam scales with different parameters. So we found that it scales approximately linearly with A0. So we measured our charge as a function of A0, which again is like the square root of intensity. This is for the 6 millimeter nozzle and a plasma density of 5 10 to the 18th. And we see this approximately linear scaling. This same trend was observed for 6, 4, and 10 millimeter diameter nozzles at a variety of different plasma densities. So this is a very robust scaling across a wide set of parameters. And then we actually identified the ideal regime for producing high charge electron beams for this self-modulated laser wave field acceleration based laser plasma accelerator. And that's for plasma densities of 110 to the 19th per cubic centimeter or less. So again, plotting charge this time versus plasma density for a 6 millimeter nozzle. And we see that we get a linear increase with plasma density for both our lower intensity case, our A0 of 3, and we see that scaling increases much more quickly for our A0 of 6 case. We also extended our plasma density well beyond 110 to the 19th. This is for a 10 millimeter nozzle A0 of 5. And we see that though our charge is linear up to that 110 to the 19th place point, it then plateaus. I will note here that this scaling gave us our electron beams with charges up to 707 plus 429 or minus 224 nanocoulombs. So that point was measured here. And this observed charge exceeds the next best result from a laser plasma accelerator by nearly an order of magnitude. So this is charge in microcoulombs for different facilities and different regimes of laser plasma accelerators. And you can see we're working in self-modulated laser wave field acceleration, which gives the highest charge beams, but we're almost a full order of magnitude higher than the next best result from Vulcan.
So that means the number of electrons is about 1 trillion electrons.
Oh,
And then it comes to roughly.
yeah, I calculated this number a while ago and I don't.
The charge is 1.6 times 10 by 19.
Yeah.
Minus 6 or 7, give you about 1 trillion electrons.
Right, yeah, it's a lot. The other thing that was very unique about this was that our laser to electron conversion efficiencies were up to 11%. And this has often been one of the downfalls cited for laser plasma accelerators is they can't get good efficiency of the drive beam into the electron beam. But if we look at our spectrum and get a weighted average electron energy at 17.9 MeV, and then if we convert our 707 nanocoulombs at that energy, we get our conversion efficiency of 11%. All right, so great. We've now made this beam with a lot of charge. I spoke about how people want to use it for X-rays. But
what size of the beam? I mean, what is the size? What is the physical size of the beam?
yeah, so where it exits the plasma, it's approximately 30 microns in diameter. And then it has about an 80 milliradian divergence. So yeah, so it is spreading. So it just depends on where exactly we want to use it. Yeah.
Oh, but still, it's less than millimeter, I guess.
Oh, yes. Yeah. And so it's ultimately the resolution will be limited by that source size. And the source size is set by the spot size of your laser. So if we were to drive with a laser with a smaller spot size, we could get a smaller source of electrons. Right. So I'm going to talk a little bit about what we've been doing with this, which is electron radiography. And electron radiography is of very high interest to the national security associations of like all the various national security labs in the US, because it's a potential path to fill the gap in visualizing fast dynamic processes in the mesoscale range of materials from milligrams per centimeter squared to several milligrams per centimeter squared. So if you look at today's workhorse radiographic probes, so when you're trying to evaluate any kind of dense or fast material, explosive products, things like that, we have different facilities that can do it, and they can evaluate different scales of aerial density based on the type of radiographic probe. So if you're looking at the very thick, so 180 grams per centimeter squared, LANL has a facility called DART, and that can probe that type of range of densities. The intermediate densities, 1 to 50 grams per centimeter squared, can be evaluated using proton radiography at LANL's Lance facility. And then if you want to look at something very, very thin, you go to Washington State's dynamic compression sector. So that's less than 0.01 grams per centimeter squared. So there's a gap here, and some prior electron radiography experiments use the electron beams from those RF linacs that I started talking about to demonstrate that electron radiography could visualize material in the 0.01 to several grams per centimeter squared range. So in here. And they showed that the gap between that very thin and the intermediate aerial density capabilities is one that ERAD could potentially fill. So the question we're asking is, can we now use a laser plasma acceleration based ERAD source to fill this gap, and particularly one that's driven by the lasers that are already attached to these high energy density facilities? So we've also done these experiments on Omega EP using the platform we developed that are producing these 0.7 microcoulomb beams. So everything's the same as what I just described, except for in our first round of experiments, in the stack on the front of the EPPS, behind our aluminum and 2 image plates, we added a series of radiography objects, and then an image plate behind it. The image plate in the front gives us the reference image of what the transverse electric beam looks like, and then behind captures the actual radiograph. So we made each of these a separate quadrant so that we could test 4 different materials on a shot. We looked at copper, aluminum, titanium, tungsten, tin, and stainless steel. So our electron beams can punch through a lot of stuff. We put, because we were interested in the resolution capabilities, we put a series of holes ranging from 0.02 inches in diameter up to 0.10 inches in diameter. And then we also varied the thickness of the object. So the smallest step was 0.022 inches, and they increased in steps of that thickness up to 0.1575 inches. We also tested, this was really cool, 30 micron lead wheel pattern that came from Los Alamos. It's kind of a benchmark resolution object for them. And one of the big questions is, if we have structure in our electron beam, can you still get radiographs from it? And the first thing we did is show that we can do that. So this is the reference image on the image plate in front of the radiography objects. So you can see that our electron beam has a lot of structure. This is the raw radiograph from the image plate behind the objects. And if we subtract this structure off from the raw image, we get this final image, which is much nicer and you can get good resolution measurements out of. We did the same thing over here, reference image, ERAD image for our different quadrants. And so that was the first test passed for our source. And the next thing we did was to measure the resolution. And we did that by fitting an error function to line out across the step in the material thickness. So this is a close-up view of one of the tungsten quadrants. So we take a box line out that's tens of pixels wide. And that box line out gives us kind of the jagged curve here. And then we fit an error function to it. This is the form of the error function. The parameters A, B, C, and D are all just fitting parameters. And D is the one that gives us our resolution. So we took this measurement for every step at every hole. And then we defined the error based on averaging multiple measurements. And then recognizing that our blur can be attributed to several factors: source size, our imaging system pixel size, if we have uncorrected multiple Coulomb scattering, or Bremsstrahlung broadening. So the measured resolution is compared to the theoretical resolution for charged particle radiography. This is theoretically what our resolution should be limited by. So 1 over the magnification times these 3 terms added in quadrature and the square root of them, where delta S is our source size. So if your target is less than a radiation length, which is the length it takes an electron to lose 1 over E of its energy, then the source size is going to dominate that 30 micron number that I gave. Delta X is scattering. So if you're getting thicker targets, then the scattering of your electron beam is going to dominate your resolution. This approximately scales as the Z of the target squared plus Z. And then delta P is our imaging system pixel size. This is the one thing we have good control over. 25 to 100 microns for the image plates in our system. So you can see right now, this is already a big limitation to resolution. So we can correct that by changing our detectors. Note that this resolution does not account for Bremsstrahlung blurring. So as that electron beam is going through a thick sample and being bent by the nuclear fields and emitting Bremsstrahlung X-rays, that is not taken account for in this resolution. So here I put Garrett's picture up. He's been working with me on this and doing the bulk of the analysis. So like every whole measurement, that was him. So what we found was that the resolution in this contact configuration, where a detector is next to the object that we're probing, degraded with increasing thickness and with the Z number of the radiography target. So that's shown here, resolution in microns versus thickness for all the different materials that we looked at. The light green dotted curve is the predicted resolution for aluminum, which was our lowest Z element, and the black dash curve is predicted for tungsten, which was our highest Z element. And so you can see that in general, the trend follows what we'd expect, with some notable outliers here at our thinnest material. Somewhat surprising that your thinnest material would be the outlier, but part of that reason is for this thickness, our tungsten and our titanium are great Bremsstrahlung converters. So they're making a lot of X-rays really efficiently, but that's limiting our resolution. But I will note, we did see clear images even through 4 millimeters of tungsten, which is very good for radiography source. The next thing we did was say, okay, we can get a radiograph when our sample is next to our image plate. Can we now do it when they're separated? So this required some modification to our experimental setup. Now we had a projected radiography object that was stock mounted, and it sits 14.7 millimeters downstream from our gas jet. We had to make it much smaller because of damage concerns for the laser. Now that it's so close to the focus, we didn't want the debris to back propagate and damage the off-axis parabola. We still had our image plate stack, this time 25 microns aluminum and 2 MS image plates. And now we're holding them on what we call the near target arm. And it lets us just move our image plate stack through a 30 centimeter range. So we could be as close as 5 centimeters and as far back as 35. This is what our target now looks like. So it's a 1 millimeter radius disc. And it's either constructed of 2 full stacks if we're shooting polyimide, which is a plastic, and then a half stack, or just 1.5 stack for other 3 materials, copper, titanium, and tungsten. We did the half stack and the full stack so we could get 2 different thicknesses on a shot. And then we have the different holes in it, 1/4 millimeter and 1/2 millimeter square, so we could get our resolution measurements again. We found that the resolution was insensitive to the Z number of the target material, which was very much a surprise. So this is our resolution in microns. This is the Z of the material. And the theoretical prediction is shown by the orange points, the orange circles. So we would expect our resolution to go up with Z. Instead, we found that it was fairly flat. And right now we're hypothesizing that this is because the Bremsstrahlung blurring is dominating the scatter in these thin samples, because they are very thin for how high Z they are. And then we also found that the resolution was insensitive to the magnification of the target. You should see it going as 1/m. And again, our data points showed no real strong trend. And what this is telling us is that the resolution is actually limited by scattering rather than the source size for these particular shots. So what we need to do is now employ magnetic optics to improve our resolution.
But it's telling you that formula is wrong.
Also, well, I mean, it does not, it's at least missing some very important components, yes. So that kind of brings us to where this work is going. For the future of this ERAD platform, we're starting to look at now driven targets, whole realm relevant work, and the addition of magnetic optics. So we recently collected electron radiographs of foils that were driven by long pulse UV heater beams. So this might be a little hard to see, but there's a driven foil that's sitting right there. And we brought in 4 kilojoule, 2.5 nanosecond drive laser to ablate that foil. And you can see the radiograph is here. It is taking a lot to kind of digest that, but we are comparing it to equivalent proton radiography experiments that were done on the same platform. And then I say in December, but this is actually on Thursday, we're doing experiments to investigate magnetic field generation in metal foils. So this is one of the things that electrons are good at, is probing the magnetic fields, as opposed to if we're probing with X-rays. And so we're seeking to further understand, there's an issue called the drive deficit in Hall realms. And this is really important for inertial confinement fusion. So hopefully we'll shed some light on that. And then finally, our collaborator, Matt Freeman, who's at Los Alamos, has designed a chicane, a magnetic optic system for our electron beam on Omega EP. And if we're able to build and implement that, that should reduce our resolution down to less than 10 microns. So with that, I'll summarize. The University of Rochester's Laboratory for Laser Energetics is growing its program in ultra short pulse laser plasma interactions. I spoke to you today about the Raman amplification and laser plasma accelerators portion of that. We have a whole group now dedicated to this field. So if you want to hear more about the crazy stuff we're doing with short pulses, invite some of them. So our Raman amplification of laser pulses in plasma is an exciting path towards overcoming the single beam intensity limit of solid state based laser amplification. And our initial experiments have demonstrated single pass Raman amplification factors as high as 12.6 and efficiencies as high as 7.4%. And then laser plasma acceleration, which again accelerates particles using these laser-driven plasma waves, boasts accelerating gradients that are 3 orders of magnitude higher than our traditional particle accelerators, and therefore may provide cost-efficient tabletop X-ray and electron sources. Our experiments on Omega EP have demonstrated beams with energies more than 200 MeV, greater than 700 nanocoulombs and laser to electron efficiencies of 11%. And then we're using those beams to demonstrate contact and projected electron radiography with our resolutions as low as 100 microns so far. Both of these, or I guess all these projects, are works in progress. So hopefully the next time I get to chat with you all, we'll have some new and updated numbers. Yeah, thank you.
I'm sure Jessica will be happy to answer some questions. You know, they have quite a few.
Yes.
Yeah, so back to the idea of wave field accelerator, right? So I'm just trying to understand it. As a laser propagates through a plasma, it creates this wave field behind it.
Mhm.
Does that wave field follow the laser pulse at the speed of light?
Yeah, so it doesn't quite follow at the speed of light. So it follows at the group velocity of the laser in the plasma. So that is typically, depending exactly on your drive laser in your plasma, something like 0.9994 C. So it's still very fast, but what we'll see is that our electrons will actually gain enough energy that they can outrun that wake structure, and then they'll stop being accelerated. So like when they reach 0.9996 C, then they've overrun that wake. If you've heard of the flying focus, people have talked about it. Yeah, one of the things we're working on with flying focus is structuring the laser so that we can truly drive that wake at C. And then the electrons would never be able to outrun that wake structure, and they should be able to be accelerated, not infinitely, but to much higher energies than the current techniques.
It's a delicate balance though, right? Because I remember watching like a talk given by one of Dr. Philosopher's students, where he said that that you cannot accelerate a massive particle with a superluminal intensity. So you kind of really have to just stay on the edge of the hoop, right?
Yeah.
Optimize it. Okay.
Yeah, and one of the things that's very challenging about if we were to drive a wake field with the flying focus is how you trap those electrons in that wake, because they need to gain enough energy that they can keep up with the wake structure. So like if you imagine your wakeboarder, right? Like if he's just standing on his wakeboard and like your boat goes past, and he'll just go up and down and he won't get trapped by it. The best way for him to get trapped is for him to have like a little velocity, and then as the boat speeds up, they go together. So this is one of the things that we've been thinking about with flying focus is, can we actually structure the light so the wake starts slow, traps a lot of charge, and then accelerates, so that we can be slow enough to load the charge in the wake, but then get it to high energies. But then exactly like you said, you can't go too fast or those electrons are just going to slip out the back. So I think there's enough work with flying focus relative to laser wake field acceleration that it could keep someone busy for like a career, because there's a lot. And we've even recently started looking at it for like muon acceleration, which is kind of the hot topic currently in laser wave field acceleration. So yeah, it's a fun time.
Any other questions here?
Yeah, I have like a kind of tangential question. So
Sure.
I know that the holy grail, as some people have described it to me in laser plasma accelerators, is to create like a tabletop lepton collider, but that there are certain people have there are certain constraints that prevent that. Like either you have enough charge but not enough intensity, or enough intensity but not enough charge. And I think there's like a third one. Like what exactly is that situation? Yeah,
that's like a very challenging ongoing situation. And part of that is that the people who are using particle accelerators keep changing their mind, partially in what they even want from their traditional accelerators. So when I entered the field, the holy grail was like a TeV electron-electron collider. And then it evolved to TeV electron-positron collider. Now they want muons. Now they want 10 TeV. So it is evolving as fast as the laser plasma accelerator field is. But you hit on a few very important things. You have to have adequate charge there, and you need to have the charge with adequate intensity. So one of the big concerns right now is because we're driving our laser plasma accelerators with lasers with like around, nominally around focus, our electron beams have a round structure, and colliders would actually like them to have like a rectangular structure. That helps with the luminosity at the interaction point. Another big constraint is for high energy, like physics applications, you need to have a very narrow energy spread in your electron beam. So I think I showed like a bajillion slides ago. Our electron beam, when we use the I won't go back. When we use self-modulated laser wave field acceleration, we'll get there. We have an energy spread that's nearly continuous. And yeah, there we go. Right. So this is our electron spectrum. We have nearly continuous energy spread. That's absolutely useless for any kind of particle accelerator. So there's ways to tune your laser to get this energy spread to be like 1% or sub 1%, but it needs to be even smaller than that for eventual collider applications. And you also need to look at your mittens, which I'm trying to think like what's the best way to describe emittance, but it's kind of like the angular spread over your energy spread, and you need that to be small as well. And so there's a lot of people focusing on getting the emittance and the energy spread down in electron beams to bring them towards kind of this, smaller scale collider. Though I think tabletop is still a little generous if they're asking for 10 GeV. It's going to still be a fairly big facility.
I had a similar question that when you say compact, how compact are these? Can you like a doctor's office or medical facility has a little source,
Right.
which probably is pretty bulky too. But can they be smaller than that size or?
Yeah, right now, so the actual accelerator itself, like the plasma stage can be really short when, right, then you need your laser. Yeah, but like the laser that I used in grad school, we had our smallest plasma source was 180 microns and we could produce 200 MeV beams in it. And our laser was like maybe the size of like one, like that portion of the room. So it was not as big as a Linac, but it's not truly tabletop. Yeah.
It's not going to replace the imaging facilities for the human body, for example.
Definitely not in the near future. No, there'd be I think you'd have to have a lot of development on the laser side in addition. Yeah. So if we're able to get like our pump lasers and our drive lasers all to much more compact case, then maybe.
Right. Are there any questions from the people on Zoom? If you have, you can type in the chat or you can just raise your hand or just speak up. Any way would be fine. I don't hear anything up there, so I think let's thank again.
Yeah, thank you. Thank you. One part up in the chat. Oh, that was just picture.
Thank you.